If I take a resistor, just a resistor, on its own, and I attach a voltmeter across it, I will get a reading of 0. If I take an LED and attach a voltmeter across the LED on its own, not connected to anything else, I will get a reading of 0. And here is a thermistor. Attach a voltmeter across just the thermistor on its own, reading of 0. Why? Because none of these components generate voltage. This, however, is a cell, and if I take a cell on its own and attach a voltmeter across that cell, I will get a reading, perhaps 1.5 volts, maybe. And this is a power pack. If I take a voltmeter and plug it directly into a power pack, I might get 6 volts, 8 volts, 10 volts, depends what I set the power pack on. And this is a solar cell. And if I attach a power pack across a solar cell on its own, I will get a voltage reading. Why? Because all of these components do generate voltage. When voltage is generated, we call it EMF. So in this simple circuit, the only thing generating any voltage is the cell. Everything else just uses up voltage. So if we put a voltmeter across our resistor now, it will measure how much voltage the resistor is using up. When voltage is being used up, we call it PD. Why does the resistor use up voltage? Because it has resistance. The bulb has resistance as well, and so it will also use up voltage. Now, we usually pretend that wires don't have any resistance, and we usually pretend that the cell doesn't have any resistance either, which means that they won't use up any voltage. So if we attach a voltmeter across the resistor, let's say maybe that's going to use 1 volt, and let's attach a voltmeter across the bulb, let's say maybe that's going to use 2 volts, and then we're saying that the wire here and here and here, they're not going to use any voltage, so that's 0 volts all round. And the cell, we said that the cell has no resistance, so it's also not going to use up any voltage. So here's the question. If I attach a voltmeter across the cell, what will the reading be? So we're going to attach the voltmeter to the terminals of the cell. What will that measure? Now, we have said that we're pretending the cell doesn't have any resistance, so that means the cell isn't going to use up any voltage. So you might think that the voltmeter reading is going to be 0 volts. However, it will not be. Why not? Because if you attach the voltmeter to the terminals of the cell, what you are going to measure is the total voltage used up in the whole rest of the circuit. Everything except the cell. We call this the terminal PD. Here's another simple circuit. Now, Kirchhoff's second law tells us that in a closed loop, if you add up all the EMFs and you add up all the PDs, those two totals have to be the same number. Our circuit is indeed a closed loop. let's say that the cell is a 6-volt cell. That means that our circuit is supplied with 6 volts in total. And Kirchhoff's second law tells us that the circuit must use up 6 volts in total. Now, we usually pretend, as we've said already, that the wires have no resistance and the cell has no resistance, so they're not going to use up any voltage. So it's only the resistor and the bulb that are going to use up any voltage. So they need to use up this 6 volts between them. So if I attach a voltmeter across the resistor, and let's say it measures 2 volts, well then we know that if we attach a voltmeter across the bulb, we know that it will have to read 4 volts. What happens if you have more than one cell in the same loop then? So here we've got the top cell has an EMF of 3 volts and the bottom cell has an EMF of 1.5 volts. It's helpful now to draw arrows to show which way each cell is pushing the current. Now this is the positive side and this is the negative side, positive, negative. Current flows from positive to negative, so that means that this cell is pushing the current out the positive side, and this one is pushing it out the positive side. Okay, if we trace with our finger now around this loop, we can see that both cells are pushing the current in the same direction. So the total EMF is 4.5 volts. And Kirchhoff's second law tells us that the total EMF must equal the total PD in a closed loop. So if this circuit is being provided with 4.5 volts in total, then it also needs to use 4.5 volts in total. We were pretending that the wires and cells have no resistance and use no voltage, so once again the resistor and the bulb would need to be sharing the 4.5 volts between them. If we draw the arrows to show the direction the current is being pushed, out the positive, out the positive, this time we can see, if we trace around the loop, that these two cells are working against each other. They're not pushing in the same direction. So what happens here then? Which direction will? Well, the top cell is 3 volts and the bottom cell is only 1.5 volts. So the top cell wins and the current will get pushed this way round the circuit. So in this case, the total EMF is 3 minus 1.5. The minus sign is there because this cell is working against the other cell. And once again, Kirchhoff's second law tells us that the total PD has to equal the total EMF. So this circuit needs to use up 1.5 volts in total. The wires aren't using any, the cells aren't using any, it's just the resistor and the bulb again. So if we measure the voltage being used by the resistor and find that it's 0.5 volts, then we know that if we measure the voltage across the PD across the bulb, we'll have to find that it's 1 volt. We're about to look at recharging batteries. So before we leave this circuit, one last word on cells that are the wrong way round, like this cell at the bottom here. We've said that if the current is flowing this way through the cell, then it's going to gain 1.5 volts. However, in this circuit, the current is actually flowing the other way, backwards through the cell, which means that it is losing 1.5 volts. So this cell is actually not giving voltage, it's using up voltage. So it's acting like a normal component with a PD of 1.5 volts across it. Okay, so now we're going to look at charging a flat battery, or actually I need to say charging a flat cell because I only have one. Remember, one is called a cell in physics, and if you have more than one, it's called a battery. Okay, so here's my cell, and let's say that when I bought it and it was fully charged, then it provided 6 volts. Its EMF was 6 volts. But now it has gone flat. That means the energy that was stored inside has been used up, and that makes the EMF drop. Now, a flat battery doesn't actually have an EMF of 0 volts. It never actually gets to 0. But let's say maybe it's dropped to 1.4 volts. But I want it to be back up to providing 6 volts again, so I need to recharge it. The way you do that is you attach it backwards, the wrong way round, to another cell that has a higher EMF. So here is a cell that is providing 6 volts of EMF, and I'm going to attach them into a circuit, but with them not working the same way. I'm going to put a resistor in, and you'll see why we're doing that when we look at an exam question slightly later on. Okay, if we first of all we need to work out which way they are pushing the current. So the bottom cell is pushing the current out the positive, top cell is pushing the current out the positive, and as you can see, I have drawn it correctly. The two cells are not pushing in the same direction. Okay, so which direction is the current actually going to go? Well, this cell at the bottom has the larger EMF, so it wins, and the current will in fact get pushed this way, which means that, as we said before, the current will be pushed backwards through the flat cell. This is why the flat cell charges back up again, because when you push current backwards through it, it's using up energy. Where is that energy going? It's getting stored in the battery again. Right then, Kirchhoff's second law tells us, as usual, that the total EMF in a closed loop is equal to the total PD. The total EMF is this. Remember that if a cell is working against the other cell, then we minus its EMF. And now let's think about the total PD. The cells don't have any resistance, so they don't use any voltage. The wires don't have any resistance, so they don't use any voltage. The only thing that's using any voltage is this resistor here. So the only thing that has a PD is voltage used, the only thing that has a PD is that resistor there. So the total PD is actually this PD here. Let's call it PD across the resistor. PD across the resistor, the only PD. Right then, so we can see that the PD across the resistor is 4.6 volts. So this reading here will be 4.6 volts. Now notice that we can do a bit more calculating here because we know the resistance of the resistor as well. What does that mean? It means we can calculate the current. Use Ohm's law. The PD across the resistor and there's its resistance. So we get a current of 0.46 amps. So if I was to put an ammeter in there, it would read 0.46 amps. So we've just worked out that the PD across the resistor is, in our circuit, 4.6 volts. Right. Earlier we talked about something that gives us a shortcut here. So sometimes it will be easier, be quicker to deal with a battery charging circuit like we're going to do now. So we have said that the flat cell, in fact, it's not providing 1.4 volts. It's actually using up 1.4 volts as it recharges. So we said earlier that that means it is behaving like a component, some other component that is not providing 1.4 volts, but that is using up 1.4 volts. And when you're using up voltage, we call that PD. So our flat cell is behaving like a component with a PD of 1.4 volts across it. Okay, this gives us we will get the same result, but if we look at Kirchhoff's second law now, total EMF equals total PD in a closed loop. So the total EMF as we have the circuit drawn now is 6 volts, and the total PD is going to be the PD across the flat cell plus the PD across the resistor, and so we can see that that needs to be 4.6 volts. So in this method we get the same result. The PD across the resistor again is 4.6 volts. That's right, that's what we should have got. So this is sometimes a useful shortcut. Treat the flat cell like a component instead of a cell. Treat it like it's got a PD instead of an EMF, and sometimes that makes the cut. We're going to look at an exam question now, and this is OCR Physics A, June 2015, and it was G482, and we're on question 3. All right, so we have a battery charger on the left, and here's the cell that it's charging up on the right. So the cell on the right wants to push the current this way, but if you are charging a cell, you are actually pushing current the other way. So we know that the current is actually being pushed backwards through the cell. And if the current is being pushed this way, that means it's coming out, current comes out the positive, so this must be positive and that must be negative. So state whether the terminal X is positive or negative. X needs to be positive because the current gets pushed out the positive, round and backwards through the cell that we want to charge up. Mark the direction of the current, label your arrow I, done it already, give a reason for your choice. We write this last part of the question asks us to calculate the terminal PD between X and Y. So there's X and Y, that's the battery charger, so it's asking us to find the terminal PD of the battery charger. If you haven't revised internal resistance yet, then I suggest you go watch that video and then come back again. I'm going to use the shortcut that we discussed earlier to make this question much faster. So I'm just going to redraw the circuit on the left. Now you can see that the battery charger doesn't have any resistance, no resistor in that box, but the cell on the right does. it's got this much resistance, 0.9 ohms. When I've redrawn the circuit, I'm just drawing the resistor out here like a normal resistor. The other change is that, as we said earlier, a cell that is having current pushed backwards through it, in fact, this cell it's not providing 1.5 volts, it's actually using up 1.5 volts. So I've redrawn the cell as just some component, don't care what it is, but it's got a PD across it of 1.5 volts. It is using up 1.5 volts. Right then, this resistor, as it is now, we can calculate the voltage that it is using up as well. Earlier in the question, you can't see because it doesn't fit on here. So earlier in the question, it tells you that the current in the circuit is 450 milliamps. So there's our current, and we know that the resistance of the resistor is 0.90 ohms. So we can calculate. So the PD across the resistor is the current through it times its resistance. So that is 0.405 volts. So now we have that the PD across the resistor is 0.405 volts, no rounding till the very end of the question. The terminal PD is the total voltage used up between the terminals, or rather, if you come out one terminal, go round, back into the other one. How much voltage has been used up in total around that yellow line? Well, it's nice and simple. In fact, it's this plus this. So the terminal PD is just that's 1.9 volts rounded now to 2 sig fig. So you can see that the shortcut makes this question actually quite quick, which is why it's only worth 2 marks.